Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 30th, 2025, about 5 days ago. It introduces a framework called World Model-Inspired Sarcasm Reasoning, which decomposes sarcasm detection into 5 cognitive steps using specialized agents, consistently outperforming standard large language models on major benchmarks. The paper is titled World Model-Inspired Sarcasm Reasoning with Large Language Model Agents. As we'll see later, the results are really impressive, showing that explicitly modeling the gap between literal meaning and social expectations is key to understanding sarcasm. So, Figure 1 breaks down the framework's architecture, which mirrors human cognitive processing. On the left, the input text is analyzed by separate agents. The literal meaning agent extracts the surface sentiment, while the context constructor and norm reasoner determine the actual negative situation. Moving to the purple section, the inconsistency detector calculates the mathematical gap between that positive literal value and the negative expectation. Below that, the mental state intention reasoner adds a theory of mind analysis to confirm the speaker's intent, and finally, all these scores flow into the decision block on the far right. Alright, Table 1 formalizes this structure by mapping specific agents to the components of a cognitive world model. The top rows align the observation, latent state inference, and state prediction with the literal, context, and norm agents respectively. Crucially, the fourth row identifies the prediction error as the domain of the inconsistency detector, which treats sarcasm as a measurable deviation from expectations. Finally, the bottom row shows that the decision step combines the intent agent's insights with a logistic regression arbiter to reach a conclusion. Well, having established the theory, Table 2 presents the concrete results across 3 sarcasm benchmarks, IAC versus 1, IAC-V2, and Semival 2018. The top section lists traditional deep learning baselines like BERT, while the middle rows cover large language model methods, including GPT 4.1 Mini equipped with strategies like chain of contradiction. Interestingly, sophisticated prompting doesn't always beat the base model here. However, looking at the bottom row, WM-SAR consistently sweeps the board. It achieves the best performance on every single dataset, reaching an average accuracy of 75%, which is a clear step up from the competitors. So, Figure 2 breaks down exactly which parts of the framework are doing the heavy lifting via an ablation study. The charts display accuracy in the top row and macro F1 scores in the bottom row. Look at the green bars in the average column on the far right, which represent the model without the intention score. Performance drops drastically here, falling from over 70% to below 60%. This confirms that while inconsistency cues, identified by the orange and red entries in the legend, contribute to the score, the theory of mind agent is the single most critical component. Okay, beyond accuracy, Table 4 examines the computational cost by measuring the average inference time per sample. The first 4 rows show that standard prompting strategies, like GPT 4.1 Mini and chain of contradiction, are extremely fast, averaging around 1 second or less. However, the competing multi-agent framework, CAFI, is computationally expensive, taking over 21 seconds to process a single sample. By comparison, WM-SAR strikes a balance at approximately 7.6 seconds, which is significantly faster than CAFI, while still supporting the complex reasoning structure we discussed. Alright, shifting from efficiency back to the inner workings, Figure 3 visualizes the decision logic by ranking the top 10 weights in the logistic regression arbiter. The chart shows that the most influential features, represented by the tallest bars on the left, are all transformations of the intention score, denoted as T. For instance, the sigmoid of T carries the highest weight, far outpacing the inconsistency metrics labeled with D on the right. This hierarchy proves that while the model tracks contradictions, the theory of mind agent's assessment of intent is the primary driver. Wrapping up, 2 key takeaways stand out. First, decomposing complex pragmatic tasks into specialized cognitive agents outperforms generic black box models. Second, explicitly modeling the gap between literal meaning and human intention is essential for true understanding. This suggests a promising future for interpretable, structure-aware AI. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.